Hi Lena, welcome on board this session. The topic of this session is aerodynamic forces and moments. This particular topic is entitled to the subject flight mechanics. The target audience for this session are GATE Aerospace aspirants, aeronautical and aerospace engineering students. We have been following the GATE Aerospace Engineering syllabus for flight mechanics and we are in the last portion of the basics category of this syllabus. In the previous lesson, we did see about the roll, pitch and yaw controls. And getting an outline of this session, we'll be first knowing about the forces acting on an airplane. Further, we will be focusing on aerodynamic forces and these moments. And as a further portion, we will be defining, deriving, and talking about the necessity of these aerodynamic forces and in particularly the coefficients and why we use them. At As a last measure, we will be also knowing the physical significance of these coefficients and how do we attain it by using the airfoil tools. Let's get started. So, talking about forces on an airplane, in general, when we talk about forces on an airplane, we'll be discussing about the four major forces acting on an airplane. Those are the lift, drag, thrust, and weight. So when we try to categorize these forces based on the type of it, the lift and drag can be categorized as an aerodynamic force. So we will be knowing what is an aerodynamic force in the further slide. Before that, we have thrust and weight. So thrust can be categorized as either a reaction force or an aerodynamic force, normally known as a propulsive force. So why is thrust an aerodynamic force? We know it is actually dealing with the propulsion part, but why is it an aerodynamic force? It is a question of interest. So here, thrust force is generally created by propellers or jet engines. This is a common source of thrust. So whenever the thrust force is created by propellers or jet engines, it is basically creating by the action on the surrounding air. It can also be categorized as an aerodynamic force. As this thrust force acts on the surrounding air, this is also categorized as aerodynamic force in some literatures. Now, when we get to weight, it is a body force. Body force is nothing but a force which acts all over the volume of the body. So, this has nothing to do with the aerodynamic moments and everything. So, that's why it's a body force. And we will be majorly focusing on lift, drag, and the moment of it. Now, getting to the core portion of this session, aerodynamic force. So, what is an aerodynamic force? Consider that when a body is in motion, or the body is stationary and the fluid is in motion. So, this is known as the relative motion. The first case, when the body is motion, is an example of the real case scenario like an airplane flying. And in the second case, when the body is stationary and the fluid is motion or in moving condition, is example of wind tunnel case. So here, whenever a body is in relative motion, there is a force exerted by the air on the body. So this particular force is known as the aerodynamic force. So as I said, aerodynamic force is nothing but the force exerted on a body by air or a gas in which the body is immersed and is due to the relative motion between the body and gas. There must be some source of it. So basically, there are two sources of aerodynamic forces regardless of shape. So these two forces are either it has to be shear pressure force or the shear force. So when we categorize it based on the direction or type of it, we can categorize it as normal force and shear force. So normal force is nothing but the force acting in normal direction. So here we see that pressure on the surface of the body is acting in normal direction, that is perpendicular to it. And shear force we have acting in the parallel direction. So shear force is nothing but which is caused due to the viscosity of gas. This is also known as a screen friction. And we had to know that comparing to pressure force, the shear force is totally small. Like if we have a shear force of 1 Newton, the pressure force will be of 2 newtons or 4 newtons. So comparatively, the shear force is very small compared to the other forces. Now, how do we determine it? So how do we determine an aerodynamic force? So if we require an aerodynamic force, the total aerodynamic force can simply be attained as a summation of the pressure and shear uh, stress distribution or force distribution integrated all over the total exposed area. So this total exposed area is nothing but the wetted area. That is, wherever the air is in contact with the surface, it is known as the wetted area. Now, talking about the summation of pressure and shear stress, so we have some area. We know that pressure is nothing but force by area. So in this particular instant, we require force. So what we are estimating is the aerodynamic force. So we require force. So for obtaining the force, we can simply multiply the pressure times area. So we will be remaining with the force here. Now, when I consider the case of an airfoil, let me take a small area ds. So there are two forces acting on the normal force and the tangential force, which is parallel to it. So when I take the case of summation, so here, as I said, force is a product of pressure times area from this formula. We can write it as pressure times, now we are adding the pressure force and the shear force. So here, when we get to the pressure force term, the pressure P times area, and additionally we are adding or multiplying it with the normal force. Similarly, for the case of shear force, we are taking the shear force times area and the kind of the force, that is a tangential force. And here it is interesting to note that the sign of pressure force integrated is negative. So why is it negative? So as we did see in the previous slide, here the pressure force is acting towards the object, that is in common case you can consider this as compression force. It is going to compress the object if it is not isn't exerting an equal and opposite force. So this is why we have a negative sign over here. There are multiple reasons which you can go through in the literature. So here we did add the force due to pressure and we added the force due to shear or friction. Now getting into the core essence of this session, the aerodynamic forces, lift, drag and moment. So in the previous case we did solve it based on the normal and tangential force, but for the case of this session we require all these terms in lift, drag and moment. So what are these lift, drag and moment? So based on this normal and tangential force, a resultant force R can be generated or is in generally generated, which is the resultant of the normal and the shear force. So or the tangential force. So this has in general two vectors. That is, the aerodynamic force or resultant force can be resolved into two forces or two vectors, the parallel and perpendicular to the relative wind. So here the component which is acting perpendicular is known as the lift, and the component which is parallel is known as drag. So as a resultant of this, we have a moment associated with it. Moment is nothing but a rotation. So here, moment is created due to the surface pressure and shear stress distribution that tends to rotate the wing. So here we see that pressure acts all over the body. So there are vectors forcing around all over the body. This causes some kind of moment. There may be higher and lower cases all over the body. So based on it, there will be some rotation of it. So this rotation is known as the moment, and we are taking it upon this particular point. This is known as the quarter chord point, and there are multiple instances where we take about quarter chord point or about the leading edge or about the trailing edge. It depends on us. So it has to be further defined, which will be defining it further in other sessions. So as of for this session, we are having this moment. So any moment which pitches up the aircraft is known as positive moment. That is clockwise moment. You can also call it as that. Or a negative moment is a case where the nose is pitched down or the wing is pitched down. This is known as the negative moment, and this is the positive moment. So we have defined these forces. So how do we obtain it? Now we have a normal force and axial force. As I said, the normal force and axial force is over here, and as a resultant of these two, we obtain a resultant force. So this is the resultant aerodynamic force. But when we resolve it to find the lift and drag, we can resolve it into two components: the lift and drag. That is the perpendicular component lift and the parallel component drag. Now, how do we estimate it or obtain it as some value? So I am altering it. We finally require the force in newtons or some particular value. Now, as I said, let us consider a wing or an airfoil at a particular angle of attack, and there is a free stream velocity which is approaching it. So, as I said, there are normal force and axial force, which causes a resultant force. Now, if I need to obtain the lift and drag, which are the components or resolutions of the resultant force, I can obtain it by using basic trigonometry. So how do we obtain it? By using basic trigonometry. So here, if I see that the lift is nothing but a perpendicular forces. So when I add all the perpendicular forces, that is acting upwards or downwards, I will obtain the lift, the total lift. And if I add the total forces acting horizontally or in parallel motion, I will obtain the drag. This is the basic essence of using trigonometry to evaluate these forces. So here, let me use the basic law of trigonometry. So what do we require here? First, I am considering the lift. So this, we know that this is the lift, which is mentioned over here. This whole vector from this portion to this portion. So this is my point of interest. If I need this particular value, we need a relation which incorporates this particular value. So cos alpha. So here everything is in alpha, and that is angle of attack instead of theta. So cos alpha relates the adjacent side with the hypotenuse side. So considering with this alpha angle, adjacent side is this portion. So the left L is the adjacent portion and the hypotenuse is this portion. So this is the N. So here N is nothing but the normal force. So N. Now what I require is the lift. So if I require lift, I can take this N to the left hand side. Thus we obtain the first term. Similarly, we see that there is also a downward perpendicular force acting over here, and this is in negative direction, so negative lift. Now when we try to evaluate this, let me write this is the negative lift, that is lift acting in downward direction. So I need a relation which relates an opposite direction and some other direction. So here we, as per the trigonometry, sine alpha relates the opposite direction, which is negative left, by hypotenuse. Hypotenuse over here is a. So if I require the general term lift, I can write it as minus, the minus goes to the left hand side, and multiply it by sine alpha. So this is how we obtain the second term. So when we add both these terms, this and this, we obtain the lift, total lift acting on the airfoil. Similarly, for the case of drag. So here, when we resolve for the case of drag, we see that we need the parallel forces. So here I see some kind of drag that is parallel force, and here already we have some drag. So similarly, from the previous methodology, I need some kind of relation, trigonometric relation, which relates the opposite side, and here we have with the adjacent side. So when we resolve it in a similar fashion, we will obtain drag. Now, we did see that we can obtain this by using the basic trigonometric equations, but this doesn't discuss anything about variation in various physical parameters such as density, velocity, or any other kind of parameters. It is just resolved in kind of normal and axial forces and angle of attack. So here lift and drag are basically dependent on the normal force, axial force, and the angle of attack. Just that. But in reality, it's not the case, and it basically depends on various physical quantities or properties. In general, when we try to conclude all those variations, we can see that lift, drag, and moment L, D, and M basically depends on the density, the velocity, the wing area, how big the wing is, the angle of attack, of course, and the shape of the airfoil, the viscosity coefficient. And finally, we will deal with the compressibility of the air uh, by using a term A infinity. A infinity is nothing but the speed of sound, which is square root of gamma r T infinity, or similarly, you can obtain it by using another relation. So we need some relation or an equation which relates all these parameters. So here we see that lift is a function of or is dependent on the velocity, density, surface, that is wing area, the viscosity coefficient, and the compressibility factor or speed of sound. And we do know that lift equation. So this is a basic lift equation which was obtained in 19th century, and this is what we use to obtain the overall lift. So here we see that lift is half rho v square SCL. So if we use a capital L, it means on whole aircraft or a wing, finite wing, and if we use small cl, it is for infinite wing or an airfoil. So that's fine. But how did we obtain this? We know that it is dependent on all these factors, but we somehow obtained an equation which relates all this. What is the interim process between this? Let's derive the lift equation. Now here we know that lift is dependent on all these factors, and let me use a theoretical approach for determining it, known as the dimensional analysis. Before getting into it, here we see that lift is dependent on about 5 or 6 different factors. So if I need the variation of lift or some graph, I need to alter all these factors. So I need to alter one by one. That is, at first I will keep the velocity constant, or I will keep all other values constant, and I will just alter the compressibility factor, or similarly vice versa. I will keep all other terms constant, and I will vary the velocity in order to find what is the relation of lift with velocity. And it does require huge amount of resources, such as you need to run the wind tunnel for 5 or 6 different times to obtain these relations. This isn't practically possible due to cost restrictions and further restrictions, but if we somehow restrict it or simplify it so that the relation is small, we can significantly reduce the cost of experimental and numerical analysis. How do we simplify it? So that's where the role of dimensional analysis comes in. Now, let me use the dimensional analysis. So dimensional analysis is a simple approach. Let's see how we do it. So we are rewriting the same equation 1 by using some dimensionless constants. So let me take a factor outward z, which may be 1/2 times or 2 times or 3 times. So let it be a factor, dimensionless factor. Similarly, every factor, that is velocity, density, area, compressibility, and mu infinity, that is viscosity coefficient, is associated with some factor. That is, this can be of any value, 1, 2, 3, so whatever it may be. So let us give it as a dimensional constants. So here one thing we know that in dimensional analysis, what we do is we compare the left hand side of the equation and the right hand side of the equation. One thing we are sure about is lift is a force. So force in general has a unit of Newton. So Newton is nothing but kg meter per second square, I hope. So if we require an equation, we should satisfy that the left hand side of the equation's unit or dimension must match with the right hand side of the equation's unit or dimension. So when we multiply all this, the resultant value should be kg meter per second square. So this is the basic essence of dimensional analysis. Now getting to the unit and dimensions, the quantities we discussed about are listed in the first column, and we are replacing the mass, that is kg or whatever unit, into m for simplicity, and the length as L, and the time as t. So this is what we are going to use. And for physical quantities, as we see, the unit of lift is Newton, or can also be termed as kg meter per second square. So for mass, I am replacing the term with m. For length, that is meter, I am replacing the term with L. And for yes, that is area, I mean time, here it is in seconds. So here I am replacing it with time t square. Similarly, for velocity, we know that it is meter per second, that is L by t. So for density, it is kg per meter cube, which is m by L cube. So for time, here it is area, yes, it is in meter square. And similarly for dimension, meter, so it is transferred to length L. And for a infinity, meter per second, which is nothing but the speed of sound, so here L by t. Similarly, mu infinity viscosity coefficients unit is kg per meter second, and it is similarly written as m by lt. Now replacing all these terms with those units. So here lift is replaced by kg meter per second square, which is in dimensional terms ml by t square. Similarly, all these terms. So what we do in dimensional analysis is see each particular factor. So here m, the value of m or the power of m is 1. Let's resolve each one of it. So the power of m is 1, and the power of L is also 1, and the power of T over here is minus 2, as it is in the denominator. So whatever I do, the value on the right hand side, so any term which has m on the right hand side, so adding all those or multiplying all those, the power must be equal to 1. So we are categorizing or collecting all the right hand side factors which are having the value 1, or dealing with m. So first, on the right hand side, we see that m is over here and here. The power associated with it is b and f. So if we combine, or summation of the b and f must be 1. So 1, b plus 1 is equal to b plus f is equal to 1. Similarly, when we are taking the t term, so any terms which are associated with t, so here we see that t is associated for 3 different factors. So it is in denominator, so minus term. So minus a, when we add minus a, minus e, and minus f, we must obtain minus 2, which is on the left hand side. Similarly, for the case of L, the power of L is 1. So the terms associated with L, 1, 2, and 3, and 4. Here we have another fourth term. So when we add all this, so the power of L is A, the first term, in the second term it is cube, in the denominator, so it is minus 3b plus 2d, which is square root, so square, so it is 2d plus E here minus F must be, the summation of this must be 1. So this is the basic essence of dimensional analysis. That is, we are equating the left hand side and the right hand side. Now, when we solve all these equations, we did obtain these equations A, B, and C. When we solve these equations for particularly focusing for the value of A, B, and D in terms of E and F, we see that these are the three equations which we obtained. So basically, here, if we require B, we can just transfer the F term to the left hand side, which transfers to B is equal to 1 minus F. Similarly, if we require the value of A, we can transfer all the other terms to the left hand side. So here, and we will obtain in the A. Similarly, the case for D. So in the case of D, we substitute the value of A and B, which we obtained in the previous equation. So we have a value for B, that is 1 minus F. So A is 2 minus E minus F. Similarly, when we apply the value of A and B in the equation C, we obtain the value for D. So the process is totally done over here, and at last we obtain D is equal to 1 minus F by 2. So here we can see that we have obtained the values for A, B, D in terms of E and F. We can substitute these values. So when I substitute the value for A, 2 minus E minus F, similarly the other values, the equation will turn into L is equal to this kind of equation. Here when I rearrange the equation, that is collecting all the values based on the similarity of powers. So here Z is the common dimensionless constant. Rho infinity is obtained from this rho infinity 1. So the factor is 1. First I am collecting all the factors with 1. So rho infinity has a 1. So S, the area has a 1. These are both. So rho infinity and S. Similarly, V infinity is also having a constant. Now again we are collecting the values which are having E in them. So here we have a velocity, the negative of it, which means the velocity goes to the denominator. Similarly, the A term. So here A by V infinity, which is V power minus E. Similarly, when we collect all the other factors, the mu infinity, and S is having F by 2 factor. So when we collect the common F terms, this will be associated with some square root. We will obtain the equation phi. So here S square is nothing but the length of it. So here we see that L square, when we S is nothing but the area. So here when I take square of it, that is 2 times of it, or the 2 and 2 gets cancelled. S is nothing but the L square, that is the area. So when I substitute the value of L square over here, the 2 by 2 gets cancelled, so it is nothing but a L, or a distance. So this is generally known as the chord length. So when we replace this term with a chord length C, this equation turns into the Reynolds number equation. So here we see this is the Reynolds number equation, and similarly this is the inverse of Mach number relation. For further simplifying it, we are replacing these two complex looking terms with these two simple justifications. So this is the 1 by Reynolds number, and here we have 1 by ME, or Mach number, Mach M infinity. Now we look at a simplified equation. So when we further need to simplify it, we'll be taking out all the complex terms. So here 1 by M infinity, 1 by R and RE, that is Reynolds number, we can introduce a coefficient. So this is a lift coefficient. We are introducing a lift coefficient CL. So if we take out all these terms and compress it within a single coefficient, so here if we define all these terms as a coefficient of lift, so CL, we can easily simplify the equation, and we are adding a 2 to it, which is of empirical importance. That is, it is used based on the practical or experience. So here, which is used in further to relate with the dynamic pressure. Now, when we introduce the lift coefficient into it instead of these total thing, we see the equation simplifies to L is equal to half, which is obtained by CL by 2, where half is put in front. So rho infinity V square S times CL. So this is the lift equation which we are looking at, and this is what we use commonly all around the literature. This is how we obtain lift. So here we see that it is dependent on rho infinity, V infinity, and area S, or and the CL of it. And we also know that we can further simplify it. So here from the Bernoulli's equation, we know this is the dynamic pressure term. So when we replace this term with Q infinity, we'll be further simplifying the equation. So here we see that lift L is, here we have the simplified version of half rho v square, the dynamic pressure, times the wing area, times the coefficient of lift. Now we have simplified the lift dependency, and here we can see that lift is basically dependent on these three parameters. Instead of six, we have three now. Now when we further see that it is also dependent on Q infinity, and we will further be leading us to all those six. So instead of it, we are introducing the concepts of coefficients. Now, when I introduce the concept of coefficient, the benefit I have is that it is a dimensionless factor, so it can be scaled to any amount of unit without confusion. So lift is in general having some dimension Newton, and some follow kilogram meter per second square. And if we follow any other unit, it is having, let us CGS, SI, whatever unit you are following, it will be having some other value. So instead, we are introducing a dimensionless constant, and it also has some benefits associated with it. So whenever we see or use a dimensionless constant, it also restricts the dependency on fewer parameters compared to the force of it. So here we see that CL is a function of alpha, M infinity, and Reynolds number. How did we obtain it? This is from the relation which we discussed in the equation 7. So here we see CL is a function of M infinity, Reynolds number, and of course alpha. So here we see that now the total lift factor is basically restricted to these three quantities. So if we alter these three quantities, we will obtain the pattern of lift or the variation. This is how we basically do in aerodynamics lab or whatever kind of experimentation. We basically measure the CL, CD, and CM, all the coefficients of the forces instead of the forces. So here we see that Mach number M infinity and Reynolds number R infinity are known as the similarity parameters. So what is a similarity parameter? Similarity parameter is nothing but if we match the Mach number M and Reynolds number RE with same as it is as the experimental condition. Consider that I need to simulate an aircraft or experimentally simulate an aircraft flying at assume 20,000 meters altitude. So one option is that I can go to the 20,000 meter altitude and perform my testing, which is unrealistic due to current limitation in resources. But one other thing I can do it is put that model in the wind tunnel and obtain the experimental and numerical values for it. How do we do that process in wind tunnel? This is how we do that by using similarity parameters. That is, we substitute the Mach number, the Reynolds number, and we match these both conditions with the flight conditions at 20,000 altitude meters altitude. So this when we match both of these, we obtain the actual value of that particular situation in the wind tunnel itself. So this significantly reduces the cost of experimentation. Now, when we further move on to the case of drag and moment, in a similar fashion to the lift is defined as Q infinity as CL. Q infinity is a simplification of half rho v square. We can similarly define drag as Q infinity as CD. Instead of CL, we are replacing with the drag coefficient CD. And same with the case of moment, we are replacing the coefficient with moment coefficient. But here in a moment, we are having an additional term C. So what is the C which we are talking about? So C is nothing but the chord length. So why did we basically add this with the equation, the force moment equation? The reason is that lift and drag both are forces, but moment is not just a force. Moment is force times the length or the distance. So here we are having the force term. So the force term is same as it is as the lift and drag, but the additional term C is nothing but the chord length or the length. So this results in the moment, that is force times length. We know that for moment, you can see the unit, which is easy to remember, is Newton meter. This is an SI unit. So the unit of moment is Newton meter. That is, it is a product of force and length. Now, similarly, when we derive the values for CL, CD, and CM, that is, we derive the moment lift coefficient, drag coefficient, and CM, that is a moment coefficient, we can use the same relation, that is, here, this case, in a similar fashion, we replace the lift with drag and with moment. And additionally, in moment, we did know that we are having an additional length term, which is by definition. So here we see that the coefficient of lift, the coefficient of drag, and coefficient of moment are basically dependent on only these three parameters. So in the previous case, we needed to basically take 6 different set of data in order to understand the pattern or variation of lift with all those. But here we are restricted to just taking the values of 3 different data. So if we require the pattern, we will at first keep the Mach number and Reynolds number constant, and we will vary the angle of attack, and we will obtain the CL value. Similarly, the case with the CD, CM, and everything. If we need the variation with the Reynolds number, we will keep the angle of attack and Mach number constant, and we will just vary the Reynolds number. This is how we basically perform our experiments in wind tunnel. Now, talking about the physical significance of coefficient of lift and drag and moments, we need some kind of plots in order to establish this. So for this, I am going to use the Airfoil Tools. It's a website of collection of foils and plots. Now, for establishing a better knowledge, I am going to compare different kinds of airfoil and the uh, coefficients of all those airfoils. So here, now, let me take a new project. So here, let me first consider an symmetric airfoil. So we have nothing over here. Now, when I require to consider a symmetric airfoil, now for this case, I'm taking a NACA airfoil. NACA is nothing but the National Advisory Committee for Aeronautics, and NACA 0012 airfoil is a symmetric airfoil. Nomenclature will be defined in the further portion of the syllabus. So here, this is a NACA symmetric airfoil, and for this case, we have obtained so many plots. Now, when we resolve it for some particular portion, like these are for various kinds of Reynolds number. Now, I am considering this for only 2 Reynolds number in order to see what's the effect of changing Reynolds number in a plot. So here, I am taking for 2 cases the Reynolds number for 50,000 at an angle of attack 5 degrees, and here the Reynolds number of 10 lakhs and the angle of attack of 7.5 degrees. Now I have varied the Reynolds number and angle of attack. So here I can see the blue line. The plot is for NACA 0012 airfoil, and the orange plot or kind of yellow plot is for the 10 lakh Reynolds number. So here this is the case for 50,000 Reynolds number, and this is the case for 10 lakh Reynolds number. Here we can see for when the Reynolds number is higher, the variation of coefficient of lift versus alpha is also comparatively higher. And one other point of interest is the left hand side maximum range of CL or CD. So here when we see the coefficient of drag and angle of attack, we can notice that it is forming a bucket, and this is known as the drag bucket. As I discussed, um, the moment coefficient also varies with the angle of attack, and this is following some kind of pattern. So here, as I said, the particular point of interest is the range between which this varies. So the lift varies from 0 to or minimum negative to some particular 1.5 or maximum of 2, and the drag varies from 0 to some particular value like 0.12. So here this is the particular point of interest, and the CM values varies from negative value to 0.04. So this is the range, and why do we need to remember these ranges? This is because if we are calculating the value of CL, CM or CD, and if we obtain an answer exceeding this, then it is wrong. Like if we are obtaining the value of CL as 16, then it is wrong. Now here we have as I said, three different opportunities. That is, I am keeping the Reynolds number constant and varying Mach number and angle of attack. Similarly, we can do with keeping either one of these constant and either two of these constant and varying one particular thing. What is the case with a cambered airfoil? Now let me take a cambered airfoil. Any other airfoil is a cambered airfoil. So here, let me add this airfoil. Now we see the green airfoil. Now let me remove the symmetric airfoil. Here we see a cambered airfoil, and for this case, when I compare two different plots for two different Reynolds number, here I can see that the blue case is for 50,000 Reynolds number, and the yellow case is for 10 lakh Reynolds number. So here we can see the variation clearly. With a reduction in Reynolds number, the drag bucket also reduces. Similarly, the case with moment coefficient of moment, here we can see it is varying by varying the Reynolds number. So this is for the 10 lakh case, and this is for the 50,000 case Reynolds number. Now when I wish to compare these two, there is a symmetric airfoil and an NACA cambered airfoil. So here I am adding a symmetric airfoil which we referred earlier. Now when I am adding it, so here there are two airfoils. The red one is a symmetric airfoil and the green one is a cambered airfoil. Now I am only considering for two cases. There is a 10 lakh case for a cambered airfoil and comparing it with the 10 lakh Reynolds number case with the symmetric airfoil. So here both of them are at different angle of attacks. So here when I update the plot, here we can see the variation. So the yellow one is cambered airfoil, and brownish green one is the symmetric airfoil. Here we can see that the cambered airfoil is having lesser range compared to the symmetric airfoil at this particular configuration, and the maximum variation is from 0 or minimum value to 2. And similarly, the drag bucket also is reducing when we reduce the, as I said, the yellow one is the cambered airfoil. So here, for a cambered airfoil, it is having a smaller drag bucket compared to the symmetric airfoil. And here we can see the symmetric airfoil is totally lying in the range above 0 or in a minimum value of 0. Minus 0.202 to positive 0.02. But in the case of here, the cambered airfoil, it totally lies in the negative value. This is how the coefficients of lift, drag, and moment varies with the angle of attack. So similarly, you can vary different kinds of, like you can alter the Mach number, or you can vary the Reynolds number, and you can see the effect of it. So this is the physical significance of how we actually perform the experimental and numerical investigations, and whatever model it might be, we basically obtain the CL, CD, and CM values across the alpha or varying angle of attack. This basically provides us with the information of what is the pattern that lift varies or changes, and it will provide us with the results. So where to look at for getting a detailed knowledge about it. So you can basically refer the Introduction to Flight by J.D. Anderson, the 7th edition of it. The whole chapter 5 deals with this, but particularly you can focus on 288 to 300, but I recommend you to read the whole chapter for getting a better understanding. And Aircraft Performance and Design by J.D. Anderson, the 2010 edition of it, the year edition of it. The chapter 2, Aerodynamics of the Airplane, the drag polar, the particular page numbers 51 to 70 also deals with it. And I highly recommend you to go through the book. That's it for this session. I reached the summary. So we did know about the aerodynamic forces and the moments, and we did derive and know about the coefficients of lift, drag, and moment, and the necessity of it. Thank you. Let's crack Gate Aerospace Engineering.